Good morning, everyone. Thank you for being here. I'm here on behalf of the entire networking team at Google. We're part of Google Technical Infrastructure, which is, again, under the umbrella of Google Cloud right now. I'm going to talk about availability of cloud networks, cloud-scale networks. And to talk about that, first we have to figure out where are we with cloud. And unlike, I think, Fran's previous slide around the 5 stages of cloud, here we have 3 stages. And we are just crawling to sprinting in 3 stages, is the way we look at it. So Cloud 1.0, in our opinion, was virtualization. So you took your data center, you took your physical assets, you virtualized them, you moved them to be more agile, more elastic. There was a whole bunch of CapEx savings that you got as a result of virtualization, but it was also about operational savings and the ability to be, again, agile and elastic, and that's good for your business. Right now, we contend that we are actually in Cloud 2.0, where we are moving a whole bunch of those workloads to the public infrastructure. But if you think about it, we're still thinking in terms of boxes. They might not be hardware boxes, they might be virtual boxes. It's not a solid line, it's a dotted line. But it's still boundaries, it's still silos, it's still potentially a box. So in our opinion, the next wave is going to be about serverless compute. So that's Cloud 3.0, where you're thinking about applications, you're thinking about actionable intelligence, you're not thinking about telemetry, you're thinking about what you can do with that data. You're thinking about machine learning, not how to implement it, but what is it going to give you and how is it going to help your business. So no data placement, you're not thinking about load balancing, you're not thinking about OS's configuration, patching, and all of those things. You're thinking about your application and what it does to your business. And networking, of course, should move towards Cloud 3.0 as well. What does the statement mean? So again, these are some of the attributes that we think are pertinent to Cloud 3.0. The ones in blue are pertinent to networking if we are to support a Cloud 3.0 vision. First and foremost, the entire data center should be your storage appliance. So you disaggregate storage so that you can place it anywhere and it's not localized to a certain rack, to a certain machine. In fact, not even to a certain data center. It could reside across a bunch of data centers. You need to think about SLOs and service assurances. You need to think about what is it that your service is providing to your customers. And don't think about placement and scheduling and where to place things to enable that. You just state that this is what I want the SLO to be, and the underlying infrastructure should take care of it. How do you enable that? You enable that by thinking about policy, and you don't think about, again, middle boxes and ACLs and where you place them, but what is my policy that I want instantiated in this infrastructure? And all of this is enabled by seamless telemetry. Telemetry that is streaming, that is always available. It's constantly there. You're not polling, you're not setting up timers. It's always there when you need it, and it can scale up and scale down as and when you require it. But today, this talk is going to be primarily about availability, like I said. So it's about SLOs and primarily about availability SLO. So let's take a look at what a global cloud network looks like. And this is a simplified starting picture. So I came last year and talked about the networks that we have built, and primarily the application-to-application or server-to-server network, which is actually shown in this picture over here. So the things in blue, light blue, in the center are the Google data centers. And they are using a technology called Jupyter, which we've published in 2015 in a SIGCOMM paper. You can go and read about it. Above that, the orange bars represent the Andromeda virtualization platform. So this is the network virtualization platform that we have in Google. And again, this is public information that you can go and read about. The blue circle around it, connecting all of this together, is the Google SD-WAN, is the B4 SD-WAN, which, again, we talked about in 2013. And it was the first time that we talked about open flow and the usage of open flow in our networks. So this is the picture I showed when I came last year to talk about these networks. So again, the Andromeda controller is an SDN-based network virtualization play. Sits above, let's say, the fabric above in a figurative sense. above the Fabric controller, which is our SDN-based data center network. The left and the right show two distinct data centers across the globe. They are connected through this SD-WAN called B4. And there are two other control loops, the bandwidth enforcer, or the BWE control loop, that does call admission control and scheduling of traffic so that we utilize the WAN links properly. And then the TE controller that looks at traffic engineering for that WAN network. So those were the three pillars of SDN that we've used in Google that I talked about last year. So we've got the B4, the Andromeda, and the Jupiter, or which is the data center network. Now, all of these, if you think about them, they are about application-to-application communication. They are about server-to-server communication. You might say they're all Google-controlled. The endpoints are all Google. So it's very good and easy to do this in an SDN base because it's all proprietary. What about the public internet? And that's where we added the fourth pillar. So this is what we talked about in ONS. If you go and look at Amin Wadat's talk, it's also a paper that we published in this year's SIGCOMM, which is 2017. And it's about using SDN for our public internet. So what does it do? So let's zoom out a bit. So we are zooming out of the server-to-server, application-to-application space and looking at what happens when a user comes in to Google. And the yellow circle that you see circling the data centers and the B4 WAN, it's again figurative, it's not really circling those, is basically our user-facing WAN. So we have two backbones inside of Google. One is a user-facing one, and the other is a inter-data center one. And increasingly, they're actually interchangeable. But for the time being, let's assume that they're separate. You have these green things sprinkled around, which are the peering metros. This is where a user coming in through an ISP would peer and come into a Google network. And these are the points that we've SDN enabled using Espresso, which is our fourth pillar that I talked about. So what does enabling SDN on the peering metro do? Few things, and these are all advantages that you do get with SDN in general. So first and foremost, because it's SDN based, there's a centralized compute mechanism here, a controller mechanism here, which provides a global view. So you don't have a decentralized distributed view, you have a global view, and you can intake a whole bunch of signals to do smart things. So you can intake application level signals, you can intake real-time network state, and you can engineer a path from the user all the way down to the data center. If it were decentralized and not SDN based, you would get a path, any path. With SDN, we can carefully engineer the path a user might take based on a whole bunch of these signals that you see here. Again, details are in that paper. I'm not going to spend much time here. So moving on, again, like I said, we have two backbones. The user-facing backbone, B2, is in 70 plus locations in 33 countries. Roughly 25% of the internet is actually originating from Google on this backbone. The server-to-server backbone, which is the B4 backbone, which was in deep blue, is our SD-WAN, and it carries, believe it or not, more traffic than the B2 backbone because it's all server-to-server traffic, and it's actually growing at a much, much faster clip than the B2 backbone. So you see some of that traffic shown in the graph there, where from 2012 to 2016, we've seen that traffic on B4 skyrocket. It is also, the Google network is also more than a collection of data centers. So in this figure, you see the points in gray are actually our peering metros, the POPs that we talked about, which are being converted to Espresso. Actually, if you are coming into Google, there's a good chance that you're actually using Espresso already. It's been in deployment for roughly 2 years now. The blobs or the circles in yellow are our CDNs or our caches, which are scattered throughout the globe. And they are used for caching large data, so large objects, for example, YouTube videos. And the lines in blue is our fiber footprint across the globe. So that is what connects all of this together. Layered on top of that, in addition to our data centers, since we are going full steam into Google Cloud and we're investing a lot in it, What you see here are Google Cloud regions that are specifically built for Google Cloud. The ones in green are the ones that exist today, and the ones in blue are coming pretty soon. So again, at this level of scale, again, going back to the simplistic picture, things break all the time, as you can imagine, and they break everywhere. They break in every form of the network. They break, of course, in the application stack as well, but here, in every place in the network. And if you're familiar with your outage budgets and what it does to your network and your service, you do realize that if you're offering 4 nines of availability, that's roughly 4 minutes of outage time per month. 5 nines is 24 seconds of outage budget per month. Those are pretty small numbers. And one thing to note is not every outage results in a service outage. So if you've built your software stack properly, then you can be resilient to a whole bunch of these outages. But nevertheless, these are small numbers that you need to work against. So why is network availability such a challenge, apart from the fact that they are pretty small numbers? First and foremost, you're constantly evolving your architecture, or you should be. So for example, in Google on the data center network side, we've actually gone through 6 iterations of the architecture from 2004 to 2013. And the 2013 incarnation was roughly 1.3 petabits of cross-sectional bandwidth in one data center fabric. And in that time, or roughly from 2008 to 2013, we've seen the traffic in our data centers go 50x. So that's a lot of evolution within the data center. The networking software as well is evolving constantly, and we have this motto of launch and iterate, and we do that not just for our applications, but also on our networking infrastructure and software. And that you can see some of that software here that we've publicly talked about. The products are constantly evolving, and they bring stress to the network, to the infrastructure. They bring special requirements to the infrastructure. And my favorite statistic here is in red. So within a year of launch, Google Photos was capturing roughly 13.7 petabytes of photographs in all of our data centers. And out of those, 24 billion was selfies. So this is what happens when you have unlimited storage. You get tons and tons of selfies. Compounded by scale. So it's not just the scale of the data, but the scale of the infrastructure. So you see here, whether it's topology, whether it's connectivity, whether it's heterogeneity, that's a lot of variation and scale to deal with. So all of this complicates the fact that your infrastructure needs to be available, and how do you guarantee that? So this is our design trade-offs. When we do build infrastructure, what are the things that you need to look at? And these are the 3 basic things. This is the infrastructure version of fast, cheap, and good, pick 2. So in this case, you need to have availability, you need to have efficiency in your network or infrastructure, and velocity. And I'll talk a little bit about all of those. Typically, you would want to pick 2 out of 3, but why not all 3? So we should always question ourselves as to why not pick all 3? And you need all 3. You don't want to slow down on any of those 3. For example, how important is availability? An unavailable infrastructure is, well, non-existent. So it's highly, highly important. For us, an insecure infrastructure is also an unavailable infrastructure. If it's insecure, it's no use. So you need to build your infrastructure for hitless upgrades for self-validation, because when you move fast, you need to be able to validate yourself as to what you're doing. That brings us to velocity. So like I mentioned, launch and iterate has been the motto, and the velocity is the speed of iteration. So the networks themselves have to be architected for expansions, for augments, and for evolution. And evolution is not just the change in topology, but the changes in software that you roll out to enable new features and new architectures and new scale. And it's very easy to say that automation will solve all of this. But automation can be counter to availability, and we'll come to that in a little bit. So visibility, transparency, telemetry is critical. And then, of course, you need to optimize for efficiency. So you can always overbuild, you can always isolate through resource reservation, but you'll get stranding of resources. And you do need to build a general purpose shared infrastructure that is well managed and perfectly utilized. So yes, we do need all three, but how do we prioritize work? Where do we spend our dollars? And this pyramid talks about how we spend dollars at Google on all of those attributes. Like I said, availability is primary and the most important. So the most amount of money is spent in making sure that your infrastructure is available. Above that, we spend money on manageability. So if it's manageable, then you can move fast. Therefore, velocity. You can move fast, you can bring in more software, you can roll out software, you can enable new features. And then we work on stranding, making sure that things are efficient. And the last bit that we spend money on is performance. And it's very easy to talk about performance all the time, but we need to make sure that the rest of the pyramid is there for performance to be valid. So how do we make sure, or how do we figure out where the problems were in relation to our availability and what we did about it? So we analyzed over 100 postmortems across a 2-year period. Postmortems, I think most of you are familiar with, is a document you write when things go wrong. And we typically write something for things which were unseen. So you've seen it before and you still hit it, something is wrong in the way you've built your infrastructure. And 2 critical bits here, we always write blame-free. Going back to a previous talk, I think Fran was mentioning about the biology. I think making things blame-free is critical to moving the ball forward in technology and making sure that we're not pointing fingers. And making sure that every organization is actually equally involved. So these are some of the findings that we saw. So in this picture, the x-axis is the count of failure events that we saw in our network. And the 3 graphs are data center fabric, the B4, which is the inter-data center WAN, and the B2, which is the user-facing WAN. Red is control plane, green is data plane, blue is management plane. The thing that jumps out here is there isn't a single network that dominates. Roughly, they're all the same. So the number of failures that we see across all of our networks is roughly the same. There are some differences, but not eye-opening, so to speak. How long do they last? Again, the x-axis is the duration. It's a log scale, by the way. And the y-axis is the fraction of time, or the fraction of the failure events. And we're talking about time here. The red is B2. Again, B2, B4 cluster, all very similar. But the key takeaway here is 80% of the failures last between 10 to 100 minutes. And if you remember the budget, the outage budgets that we had, even a single failure can eat away your entire SLO for the year. So a failure is really, really bad. Who or what causes failures? It's not a bug. Bugs do cause failures, but that's not the critical bit. It's not the upgrade, it's not the rollout. The number one culprit is configuration. So when you're changing the network, when you're evolving the network, mutating the network, that is the number one culprit of outages and failures in the network. And the other important thing that we figured out was unrelated changes. So it's like a game of whack-a-mole. So unrelated changes, you think you're making a change here, a failure or an outage can happen in a different part of your network. So you need to be very careful about what you do. How do you achieve that? And our contention is that you can achieve all 3, availability, efficiency, and velocity, if you make your infrastructure to be intent-driven and not imperative. So the analogy I draw is like it's making a Google Assistant for networking. So you can say, okay, Google, mutate my network from graph A, which is existing, to graph B, which is my intended state. I won't go into the details. You can listen to Sam's talk, who's my colleague. He'll be talking about ZTN. But the important thing to mention here is safety. So it's easy to say we can do this using a Google Assistant-like thing and with an intent-driven automation infrastructure, but safety is paramount. So you should be able to continuously validate what's happening as you do your automation. You should be able to recognize bad behavior and pause. You should be able to have the ability to roll back if things have gone bad, and the ability to canary, so basically do things step at a time, and limit the blast radius. So what you really need is a Google Assistant which says, okay, Google, mutate my network from graph A to graph B, where each intermediate step cannot be larger than delta, which you define, and the rate of mutation cannot be larger or faster than, say, rho, where you also define that rate. And this is not everything. I mean, automation is only good as what your underlying hardware can do. So we are also looking for an SDN switch. And Jim had talked about this in a previous talk. Is basically using P4 for the runtime data plane and OpenConfig for configuration and management. And again, I'll skip this slide, but the key takeaway is performance is great, but it's only meaningful if your infrastructure is available, it's efficient, and you have innovation velocity, and you're not stuck in a rut and become obsolete over time. Thank you.